Hello everyone. In this lecture, I am going to discuss about fatigue design and analysis due to fluctuating stresses, and here also I will discuss in details about different types of fatigue failure criteria, which have a wide application in the field of design and analysis of fatigue related structural component, which is subjected to fluctuating types of loading. So, this is the content of today's lecture. First of all, I will show you some basics of fluctuating stresses related things, that is there I will discuss about characterizing fluctuating stresses. Then I will discuss about fatigue failure criteria for fluctuating stresses. Then I will discuss about modified Goodman diagrams, and finally, what are the references I use for making this lecture, that related thing in details I will discuss. So, I have already discussed about characterizing of fluctuating stresses. There I have already shown generally the stress for fatigue types of failure, generally it is fluctuating types of load. There are different types of fluctuating types of load or stresses that I have already discussed. So, there I have shown you that repeated types of loading, then reverse types of loading, then fluctuating types of loading, then sinusoidal types of loading, which is some cases I have shown non-sinusoidal types of loading also. So, here just the first of all, whatever the basic things required for this what it is called lecture, that related first I will discuss. After that, actually what happens, gradually I will discuss rest of the things. So, you see, let us consider this is a fluctuating types of load. Here you see, now we know this, it has a maximum value which I am showing, that is sigma max. It has a minimum value which I am showing, that is the you can say from baseline, that means horizontal line to its minimum stress value, that is sigma min. I have shown what is the distance of these things. Now, based on this maximum and minimum value, what we can generally get from this what it is called fluctuating types of stresses, that I am showing. So, this is sigma min, sigma max I have shown. So, based on this thing, generally for design of structural components subjected to what is called fluctuating types of stress, what are the some important you can say parameters are required based on this maximum and minimum stress value, that I am going to discuss. So, first of all I will discuss about sigma amplitude. So, I have already told you sigma amplitude is equal to your sigma max minus sigma min divided by 2. I have already told you this, you can see here itself. So, this is generally from here to here, you can say is called amplitude of this stress value. Then mean stress, it is called sigma m, or it is sometimes popularly generally told as mid range component of stress. So, mid range component of stress here I have shown. This is from this base horizontal line to here you can see to middle line of this fluctuating stress is called mid range stress component. It is actually your sigma max plus sigma min divided by 2, this you should keep it in mind. And another important parameters you need to know, another important parameters which you need to know is sigma r and sigma s. What is sigma r and sigma s? Sigma r is called range of stresses. So, range of stresses you can say. So, sigma r actually equal to your sigma max minus sigma min, this you should keep it in mind, not divided by 2. Okay. This is called range of stress, and static or steady stress generally when you can say your you can say this amplitude is 0, at that times whatever the stress value is there, that time then this is called a static stress, or you can say steady stress. So, what is a static stress? Sigma s generally is called a static stress when you can say amplitude of the stress is 0, that you can say. So, here one thing you should keep it in mind, in the absence of NOS, generally this amplitude and mid range value is considered as equal to the nominal stress value. So, nominal stress value I have already explained in details. Nominal stress value is the applied load divided by minimum cross sectional area. I have already told you in details in earlier lecture. So, I am not going in detail to discuss about this thing. So, nominal stresses amplitude, this is nominal stresses amplitude, and this is nominal stresses mid range value. So, sigma A 0 is nominal stresses amplitude, you can say nominal stresses, here you can write amplitude, okay. And this sigma m 0 you can say it is called nominal mid range component of stress. Okay. Now, if we consider the NOS effect, there generally we know a actual stress concentration factor, that is called fatigue stress concentration factor, is come into picture, that there generally you need to explain this amplitude and what it is called mean value, which is actually by multiplying you can say with nominal stress this Kf value, Kf into amplitude of nominal stress is actual amplitude of that stress component. Similarly, Kf into m 0 will be the actual mid range value or mean value of this what is called stress value. This you should keep it in mind. Okay. So, where Kf generally is called fatigue stress concentration factor, you know this thing, fatigue stress concentration factor SCF I am writing, its value is generally greater than 1, this you should keep it in mind. Now, we will just discuss about how to plot the fatigue failure you can say criteria in a fatigue load diagram, that now I am going to discuss. So, what we observe that, so when a component is subjected to fluctuating stress, so what we observe that there will be a mean stress or mid range component of stress Sm, as well as there will be a what is called amplitude value of this stress component. So, here one thing you should keep it in mind that the mean stress component generally has an effect on fatigue failure. When it has effect on fatigue failure, that means this Sm have a effect on fatigue failure when it is present in combination of an alternating component. What does it means? If there is amplitude of the stress, then only you can say this mean stress component has an effect on fatigue failure, this you should keep it in mind. Otherwise, if SA equal to 0, then generally Sm have no effect on fatigue failure, then only that times it become a static load. I have already told you, a static loads generally when you can say your or a steady load where your SA or amplitude of this value is equal to 0. There generally you can say this load is not a repetitive types of load or fluctuating types of load, that load is generally steady types of load, that means with time it is remain constant, that you can say. So, that is why here I have written a very interesting point, you should keep it in mind, this sigma m stress component has an effect on fatigue failure when there is a what it is called stress amplitude value, this you should keep it in mind. Generally in the fatigue diagram, the mean stress is plotted in abscissa. So, here I am little bit showing, then it will be very clear to you. So, in fatigue diagram I am drawing. So, in fatigue diagram this abscissa mean horizontal axis, Sm is plotted in horizontal axis and amplitude is plotted, S amplitude is plotted in vertical axis, this you should keep it in mind. So, this is called ordinate. So, it is called generally vertical axis is called ordinate and this horizontal axis is called abscissa. You know this thing. So, here generally the magnitude of Sm and Sa depends upon magnitude of I have already told you this Sm and Sa magnitude, it depends on you can say maximum value of stress and minimum value of this fluctuating stress. I have already told you in previous slide itself what how this Sm and Sa is required to calculate. So, when the I have already here again written when amplitude of the stress Sa equal to 0, then generally load is purely static, I have already told you. So, in this case generally you can say the failure criteria is based on ultimate stress or you can say yield stress, that means sigma ultimate stress or yield stress. So, this limit are plotted on abscissa, always you should keep it in mind. So, what we know Generally let us consider this is our yield stress. So, YT I am writing, generally ultimate stress is the highest stress value, that is generally more than yield stress. So, that I am plotted in this horizontal axis. So, here let us consider this 2 point I am writing like this. So, it is better I am using this black dotted line, that will be better. So, when the mean stress is 0, another case, when this mean stress, that this is our 0 point. So, you see when Sm equal to 0, then what happens? Sm equal to 0 means it will be a fully what it called reverse types of loading. When Sm equal to 0, Sm equal to 0 generally when S max is equal to minus S min, you can say, that I have already shown, that means which is a purely reverse types of loading, because Sm equal to what? Sm equal to, you know, S max plus S min divided by 2. So, if S max and S max its amplitude is same, with one is compression, another is tensile, then this Sm will be 0. So, for this case generally this is a what I have written, this is a completely reverse types of loading, correct. So, here the failure criteria is generally, always you should keep it in mind. For this case here generally failure criteria is the endurance limit AC. I have already told you, for reverse types of loading they are generally endurance stress is the, or endurance strength you can say, is the failure criteria, that is generally plotted in ordinate is vertical axis. So, let us consider this AC I am plotting as vertical axis, let this is our AC value. So, what happens? So, based on this data, there we can draw different types of what is called failure criteria line. Generally, if we draw the point, let us consider AC to S yield point, AC to S yield point, then that line has a name, that is called Soderberg line. I will just discuss this thing in next slide. If we join AC with this ultimate stress value, then this is called Goodman line. What I am telling, understand? So, similarly here some points I am just let these are the things. If the point, another line is also which is curved in nature, if we draw, this is generally called Gerber line. What it is called? GERBER, Gerber line. This is called Soderberg line. This is called Goodman line. Goodman line or Goodman failure criteria line, you can say. Now, you see here this point which is generally outside this different line, what I am telling, understand, which is outside this different line, this is the generally let's some points or experimental data you observe, which has a value of this point, let us consider, which has a value of S, you can say M and S amplitude for different SM and different amplitude value, different data point I am showing. So, here one things you can observe from these curves, this data point, if it is outside this different line, that data point generally is called failure data point. What it is called? I am writing, this is called failure point, failure point. If this SM and SA value within this different line, so depending upon the type of failure criteria, some cases this data point generally can be safe. What I am telling, understand, like what happens, the if this data point, let us A, B, C, D, E, let these data points are there, where there is this has different SM and SA value. So, what happens, these data points are safe from failure, fatigue failure criteria related consideration, because this data point is all inside the, you can say, all curved line. So, if it is inside the curve line, these are the data point which is safe data point. Due to this SM and SA value, your structure will not fail. This you should keep it in. If the data point, let us consider if the data point I am just showing, let us say data point F. So, this F data point, this is safe E based on this, what it is called, based on this Gerber line, what I am telling, understand. Whereas, this F point is not safe based on this Soderberg, or you can say Goodman line. This you should keep it in mind. So, that also I will discuss one by one in subsequent slide. So, generally this different data point whichever I am showing, this data point we can display in different way. Like one of the way here I am showing in this figure, you can see where this data point I am showing, which is based on what, the ratio of, you can say, SM by S ultimate. That means horizontal axis is represent mean stress by ultimate stress, and this vertical axis represent amplitude by endurance stress. This you should keep it in mind. This is the ratio. This way also we can plot. So, here you can see, here generally this is the line where you can say your this SM by S ultimate value is 0. So, right side generally this SM by S ultimate is tensile region, you can say this right side is tensile region, I am writing tensile zone, and this from this line left side is compression region. Already I have written this thing, this you can observe. So, what you can observe from this curve? You can observe from this curve generally this SM by S ultimate, that means this mean stress have a significant effect on fatigue failure related issue once it is tensile in nature, that you know. Actually what happens, generally to resist the, you can say, fatigue failure, what we used to do, we can use compressive types of load. If we use compressive types of load, it generally improve the fatigue failure strength, that you can say, that you know. So, that is why here I have written. So, whereas that mean stress is tensile in nature, then what you can observe, that means there is a chance of crack propagation, what I am telling, understand, where it is, if the load is compressive types in nature, then let us say there is a crack closing types of phenomena can take place, that you can say. So, that is why this tensile types of mean stress have a significant effect on fatigue failure, which generally, that is why here I have shown different types of this data point, which is the ratio of SM by S ultimate stress, you can see in horizontal axis, and S amplitude by AC is vertical axis. So, these are the ratio. So, let us consider this I am representing as A, and let this I am representing as B, capital A and capital B. So, these are the data point represent AI and BI, this way you can say. Here one things you can observe, that this BC line is generally, you can say, is represent as what it is called Goodman criteria of failure. The BC line you can represent as a Goodman criteria of failure, where generally this point is representing in terms of ratio of SM by S ultimate and SA by AC. This way you can represent. Another way also you can represent, that I will show in next slide. So, here one things you should keep it in mind, that the existence of mean stress in the compressive region has little, you can observe that on endurance limit, that you can observe, because you see all the data point in compressive zone, you can see it is, you can say, is always in same level, that you can say. That is why here I have written the existence of this mid stress, or you can say mean stress value in the compressive region has little, almost negligible effect, you can say, on endurance limit. This you should keep it in mind. That is why here in this region we have drawn a horizontal line. If we feed the data point, we can get a horizontal straight line, that is AB line, what I am telling, understand. So, in this zone always you should keep it in mind, in compressive zone, in this zone failure will be occur if the amplitude is equal to the endurance strength of this you can say endurance strength of this material. Why? Because generally you see this AB line is passing where the ratio of sigma A by AC is equal to 1. What I am telling, understand? That is why when sigma A is equal to, from this equation itself you can say sigma A equal to SE, that you can say, that is why you see when the mid range stress in is compression in nature, then failure will occur whenever this amplitude value of this stress is equal to the endurance strength of that material, as indicated in left hand side of this figure 1. You can see this is the figure on left hand side I have shown. So, in this compressive zone, generally you should keep it in mind, in this compressive zone neither a fatigue diagram nor any other failure criteria need to be developed. This you should keep it in mind, because this is only a single straight line is there. Whereas, in tensile zone you see this data is varying drastically depending upon its mean value or amplitude value, which is inclined, which is shown if we fit a curve, you can say a straight line if you draw, that is BC line if you draw, this BC line is called you can say Goodman criteria of failure line. So, to consider some other this AI and VI point, here you can draw different types of failure line. How it is, that I am going to discuss in next slide, where generally we will consider only this tensile portion, because in compression portion what we observe that here neither a fatigue diagram nor any other failure criteria is required. Here generally failure criteria is considered as when the amplitude value will be equal to what it is called endurance strength of that component, then what happens here, the failure is generally occur. This you should keep it in mind. In left side generally, that is why no fatigue diagram is required, or no other you can say failure criteria need to be developed, that you can say. So, now we will concentrate our discussion on tensile part only, because tensile part is mainly responsible for fatigue related failure, because in tensile portion generally if the load is tensile in nature, there is a chance of whatever crack propagation, and what happen, there can be, once it goes beyond a critical crack length, then generally what happens, your structure will fail due to fracture, that you can say. So, the tensile side of this figure 1 which I have shown in previous slide will be redrawn in terms of strength. The previous slide I have drawn it in terms of ratio. Here we will draw in terms of strength only. There generally this ratio of SM by S ultimate or SA by S endurance strength will not draw. Here we will draw considering the strength value itself, that I have already shown in first slide little bit. Okay. So, instead of strength ratio, here we will draw in terms of strength with same Goodman criteria together with another 4 additional criteria of failure, here we will draw. So, how many numbers of failure criteria are there? You can say for fluctuating types of loading case of fatigue failure, 5 number of failure criteria are there, you can say. So, how many failure criteria there are? 5 number of, you can say, failure criteria are there. What are those failure 5 number of different failure criteria, that I am going to show here by drawing the diagram, then it will be very clear to you. So, here instead of considering the what is called ratio, here we will directly consider the strength value itself. So, this horizontal or abscissa line represent mean stress component, and vertical line represent, you can say, amplitude component. So, here generally in horizontal or abscissa line, I am just first plotting the yield strength component YT and ultimate strength component UT, okay. And in vertical line I am plotting what it is called endurance strength. Okay. Now, once we draw the line endurance strength and yield strength, this line is called, this line is a failure criteria line, this line is called Soderberg line. What I am telling, understand, this is, you can say Soderberg, you can say this is a straight line, Soderberg straight line, you can say, which is a failure criteria. So, if this SM and SA value is, I am just considering L, A point. If this point within this line, this is safe. If the point is outside this line, let us B point, I am considering outside, B, C, D, different other points are there, B, C, D, other points are there. If it is outside this line, then this B, C, D, these are the lines which are, you can say, failure point. So, if the amplitude and mean value is outside this line, that is B, C, D, according to Soderberg line, this will be failed, your structural component will be failed. This you should keep it in mind. Okay. Now, I am drawing another line by joining this endurance strength and what it is called ultimate strength. This is also a straight line, this is also a straight line, I am just writing a straight line, Soderberg straight line. So, a Soderberg straight line generally you can say is developed in 1930, that which I have written. This is established by Soderberg in 1930, this you should keep it in mind. So, another line which is connecting the what is called endurance strength and ultimate strength, this line is called Goodman line. Goodman line. This is also a straight line and established in 1890. This you should keep it in mind. This is also another fatigue failure criteria. So, what happens, this A point which is inside this Soderberg as well as Goodman line. So, this A point is safe line, safe what it is called, it is not a failure point. If the load value is outside this line, let us this B point, then what happens according to Soderberg and Goodman, this B point is a failure point. We observed that in previous slide itself, there are different data sets which we generally got from experimental observation. There we observed that this data set has different types of point based on different types of steel material, you can say. So, you see it is generally which have a variation generally which is not following this same straight line types of things. That is why what happens, you can say in 1874 generally the Gerber, one researcher who generally established a, you can say, fatigue failure criteria based on a, you can say, parabolic line. What I am telling, understand, what Gerber drawn, that I am going to show, who generally try to accumulate all the point, you can say, inside the what it is called, inside this is line. So, this is a parabolic types of line which is developed by Gerber. What I am telling, understand, that is why it is called Gerber line, which is a parabolic line which is established, you can say, 1874. What I am telling, understand. So, these are three failure criteria I am showing. Apart from this thing, another two failure criteria also we used for fatigue analysis due to fluctuating loading. What is that? One is called ASME elliptical line. ASME elliptical line generally you can say this I am drawing by red color. ASME elliptical line is drawn by connecting, you see, endurance strength and yield strength value. This is developed by ASME, which is a elliptical line. What I am telling, understand, elliptic line. So, this is another failure criteria. ASME means American Standard of Mechanical Engineering. Okay. Apart from this thing, there we use another what is called line. That line has a name that is called Langer line.